Last time we were trying to classify surfaces whose canonical bundle is not Neff. So that we could write down this dichotomy for once you blow down all your -1 curves, whether kx is Neff or not Neff, we get a different classification. So we were completing the not Neff classification. And our strategy was to look at the cone of curves. So in our cone of curves, we have, I guess here I really should write n lower one, but we're viewing them as both curves and divisors. We have our kx equals 0 hyperplane. And because of our assumptions, we know that there's some of the cone of curves on this kx negative side. So this is the less than 0 side. And then maybe there are also some curves on the positive side, but we don't really care about those right now, at least. And I mentioned the cone theorem, which tells us that the structure on the negative side of this cone is nice, but we won't actually use that today. But that will be one of the main theorems that we'll prove in higher dimensions shortly. Okay, so then our strategy was to say, let's look at some ample. So let's say a equals 0, where a is ample. And then we'll write down the divisor rkx plus a, where this r is exactly what we need to hit the boundary of our cone. So this r will be, or sorry, this L with this coefficient r will be Neff because we've just hit the boundary. So we have all the curves on this ray that we're touching intersect 0, but it's still on the positive side. So kind of every effective curve intersects L non-negatively. And then I stated these two pretty important theorems that we'll prove later in the course. And right now I just want to illustrate how we can use them. So our first theorem was the rationality theorem, which was that this particular R, the one that makes this divisor Neff, is rational. So so the supremum over all t, such that t kx plus a is Neff, is actually a rational number. So that's the first key theorem. And then the second key theorem, the base point freeness theorem, I'll write it in this notation now, and then at the end of this lecture, we'll see a generalization, which is what we'll actually prove later in the course, is that if we have a divisor of this form, where R is rational and L is Neff, then L is semi-ample. So some large enough multiple is base point free. Okay. And so now our strategy was to pick some generic A and approach the Neff cone with this L, such that when our intersection of L equals 0 with our Neff cone is just a single ray. And we'll say more about exactly how you do this when we prove the cone theorem that gives us the structure of this cone. And so by single array, I mean the non-negative span of some class C, or maybe I'll call it B. And what this buys us is that this ray will be extremal in our NEX, which means that if V1 plus V2 is in this ray, where each of these vectors are in the cone, then both of these are actually in the ray. So you can see that from the picture, that if you're on one of these kind of vertices of this, then you satisfy this property. So now for this L, by the base point freeness theorem, we get some morphism for some large enough multiple of this L from our surface X to Z. Because this is a base point free linear series, then we know that a curve C is contracted by phi if and only if the numerical class of C is in this ray. And what this buys us is that, or the extremality of R, what this buys us is that this actually implies that these curves C have to be irreducible. Because if you have some curve in a fiber, and you can write that curve as like C1 plus C2 inside of the fiber, then you can check that the C1 and the C2 can't have the same numerical class as C if they're actually two different curves. I'll draw a picture. So if my fiber looks like this, then you can just check that C1 and C2 can't be numerically equivalent to C, which is what would have to happen if they're in the same ray as R. So it can't be numerically equivalent to a multiple of C. Okay, so we have this contraction morphism, and we know that the fibers are basically irreducible curves, or covered by irreducible curves. And now we can classify the various possibilities in the case of surfaces. So again, we'll come back to these type of contractions when we prove the full Conan contraction theorem, and I'll say more about maybe this fact. But now we have some cases depending on the dimension of Z, where a contraction lands. So if the target of this linear series is a surface, so if the Z is two-dimensional, then what do we know? Well, if we have a curve in the fiber of this phi for some p in Z, which is two-dimensional, then we had this fact from the Hodge index theorem that implies that C squared is negative because it's the fiber of it's in the fiber of a birational map. So this was Hodge index. But we also know this C is on one of these rays on the K negative side of the cone of curves. So we also know that Kx dot C is negative. And then this was a lemma we talked about that I think I gave as an exercise, which implies that C is actually isomorphic to P1 and C squared is minus 1. So this is using a junction plus some computations of the genus. So that tells us that we know what this phi is. This phi has to be the contraction of a minus 1 curve. So it's this morphism in Castelnuovo's theorem. It's a blowdown. So then and now using this observation that R is extremal, we also know that it has to be the contraction of just a single curve, because if we had some other curve that was disjoint from C that's also getting contracted, then that other curve will not be numerically equivalent to C, so that would be on some other ray in any bar. So each of these contractions corresponding to a single ray have to just contract one curve at a time. So then we know that phi is exactly the blowdown of 1 minus 1 curve. So in particular, these don't happen if we're already on a minimal surface. But it also says that this Castelnuovo's theorem also falls under the same formalism of these extremal contractions, these contractions of rays on the negative side of any bar. Okay, and then if the dimension of Z is 1, so then phi is some map onto a curve, and in fact Z has to be smooth because X is smooth, in particular normal, and these semi-ample contractions you can check will map to a normal curve, or if they don't, just take the normalization, it'll factor through it. So we can assume that that Z is actually smooth. And so if we look at the fibers here, they're irreducible. Kind of from this picture up here. And we also know that a fiber, because it's the fiber of a map to a curve, we know that it squares to 0. So if we have some irreducible curves that square to 0 and satisfy that kx.f is negative, because again they're on the negative side of any bar, then again this implies that these are P1s, or at least the reduced fiber is P1. So it's possible that you have some non-reduced fibers, and then maybe I'll leave it as an exercise that if you work a bit harder with these intersection numbers in the adjunction formula, that actually every fiber has to be reduced. So yeah, leave this exercise. Okay, so in that case, this phi is what I called earlier Fano vibration. But we'll sketch a proof in a second that actually, even better than that, it's a P1 bundle. So it's a projective bundle. Okay, i.e. a ruled surface. And then finally, if the dimension of Z is 0, then phi has to just be the map to a point. But then what does that tell us about our canonical? That tells us that A plus RKX is equivalent, or maybe some large multiple of this, the large multiple we need to take to make this semi-ample, is equivalent to the pullback of some divisor on a point, but that's just a 0 divisor, so this is 0. So that tells us that up to taking some large multiples, MRKX, or maybe minus MRKX, is equivalent to MA is ample. So X is Fano. Since minus KX is ample. Okay, and again, here we can say a bit more using this the fact that this R is extremal, we can actually get that, and I'll sketch an argument for this part too, that the Picard number of X is 1, which when you combine it with all the other statements, and some Hodge theory will actually imply that X is P2. But at the very least, we get our kind of rough classification that you either end up with something of codary dimension 2, or something of dimension 2, or you end up with a Fano fibration, or you end up with an actual Fano variety. Okay, so then we can finish our classification. So in our theorem, I'll summarize as suppose X is a smooth projective surface. Such that the minimal surface we get by contracting all -1 curves such that when we contract all -1 curves, we end up with something where KXM is not Nef. Then either XM is a ruled surface, or XM is P2. So in particular, our original X was a rational surface. And then moreover, I think last time I stated this as an exercise, the codary dimension of X, which is the same as the codary dimension of this minimal surface, is actually -infinity. Using these two cases, you can just check that in both the ruled and the P2 case, the codary dimension is -infinity. Okay, and so the proof of this is just using what we said above. So take our minimal model. Since KXM is not Nef, then we can find one of these extremal contractions. And by our classification, either this extremal contraction is the blowdown of a -1 curve, but we're assuming XM is minimal, so it can't be that. So that tells us that this is either a P1 bundle or XM is Fano. And now we have to check that in the P1 bundle case, you're really a projective bundle, and in the Fano case, you're really P2. So case 1, this Z has to be some smooth curve. Again, by factoring through the normalization. And we're over an algebraically closed field. And so we can use this famous result sense theorem. Implies that at least at the generic point, at least on the function field level, that kind of looks like codary dimension. If we look at the generic point and look at the generic fiber of our minimal surface, this is some genus 0 curve over this function field, and then sense theorem tells us that it actually has a rational point. So there exists some rational section like this, which implies that this generic point is actually P1 over this field. And that tells us that by taking the closure that we actually have a section of phi. And let's take its image to be D. Okay, so what that tells us is that we have this divisor that's horizontal in the sense that D dot any fiber is actually 1. right? So we have these P1 fibers, and this D will be something like that. And we're going to use this D to produce an isomorphism between phi and a projective bundle, and a projectivization of an actual vector bundle. So we're going to use the divisor to produce the vector bundle, basically. And because like being a projectivization of a vector bundle is a local condition, we really just have to check this, that in a neighborhood of a point on Z. So basically what we want to check is that for each point P in Z, we can find some neighborhood U and an isomorphism phi inverse of U with P1 cross U over U. And maybe I'll stop writing the M and just X from now on will be this minimal surface that, so we've already blown down the -1 curves just for convenience. Okay, so this is what we want to check. And we're going to do this using the existence of this section. So yeah. Okay, so let's consider the following exact sequence. Where F is the fiber over our point P. And D is this section. So here's just the standard exact sequence coming from twisting. But using that the fiber is P1 and using this condition that D dot F is 1, then we know that OF of D has to be a line bundle of degree 1 on P1, so it has to just be O of 1. So now maybe the first claim is that if I take global sections here, then for R very large, this map is actually surjective. Okay, and the idea here, it might not actually be true that H1 of this next term vanishes, but you actually just check that the H1 map stabilizes, that the H1 map becomes constant by checking how things grow. So I'll leave that as an exercise. Okay, so now once we have this surjectivity, then we can pick some V in here that's two-dimensional and maps isomorphically onto H0 of O of 1. But now this V gives us some linear series. It's two-dimensional, so it gives us a linear series to P1. We get some rational map to P1. But we know that when we restrict this linear series to our fiber, then we get a surjection onto global sections of O of 1. But this is base point free on F. So whatever base points this linear series has, they're contained away from f itself. Because by this surjectivity, we can take any polynomial, any linear function on our fiber and then lift it to some section in this V. So if all these lifts vanish, they're not going to vanish on F. They're going to vanish somewhere away from F. So we can find this neighborhood that contains F where V has no base points. And I'll call it phi inverse U because once we find some neighborhood of F itself, then we can shrink it and check that it's actually the preimage of a neighborhood of on our curve. So up to shrinking. Such that this linear series phi sub V restricted to phi inverse of U is a morphism. And so now we look at that. So we have phi inverse of U with a map to P1 given by this linear series restricted. And we also know that this map to P1 is an isomorphism of F with P1. Again, because V restricts to F to just be the linear series O of 1, which induces an isomorphism of F with itself. Or another way to say it is that whatever phi is, it's degree 1 on the fiber because it restricts to this O of 1 on the fiber. So it's a degree 1 map on the fiber, so this has to be an isomorphism. So now if we product with U, we get our linear series times our original map, which goes from phi inverse of U to P1 times U. And this now is some map between normal varieties that's an isomorphism on the fiber over our point, which means it's an isomorphism on some neighborhood because everything it's flat over this U and everything's normal. Yeah, so this implies that maybe after shrinking a little more, phi V times phi is an isomorphism in some neighborhood of the fiber. Yeah, because everything's normal and that's some bijection near the fiber. Okay. So that tells us that every point has a neighborhood where it really is a projective bundle. In this case, a trivial bundle. And so then to produce your kind of global one, you look at the transition functions for these different neighborhoods where it's trivial, and that'll give you some vector bundle that this whole thing is a projectivization of. Okay. Any questions about that? Sorry, that was kind of a sketch lacking some details, but. Okay, so that gives us our first case that that when we're this Fano fibration, we're actually a ruled surface. And now our second case is a little trickier, so I'll be even more vague in the sketch to see that you're actually P2 in the other case. Okay. So we know here that minus kx is ample, but we also know that this phi contracted an extremal ray. And so that tells us that the Picard rank of x is, and remember this was the dimension of n1 real has to actually be 1. And again, because if you had a larger Picard rank, then, or really, what is it saying? This is saying that every curve on X has to be on the ray spanned, has to be on our extremal ray, because phi is this extremal contraction. And every curve on X is in the fiber of the map. So every curve is numerically equivalent to something on our ray, but that's exactly saying that our whole Néron area is just one line, because up to numerical equivalence, everything is on the same ray. Okay, so that's the first observation. And then we also have some properties of the Hodge numbers. So 2, if we look at cohomology with coefficients in the structure sheaf for I greater than 0, this is the same as cohomology of X. I'll write it like this because we want to use a vanishing theorem, which we'll prove later in the course. So O is the same as the canonical plus kx, plus minus kx, but this is ample. And now we can use the Kodaira vanishing theorem. Which is actually one of the ingredients when we prove the base point freeness theorem. Actually, we'll prove a generalization of the Kodaira vanishing, the Kawamoto-Vivek vanishing theorem, but I'll just state it here. In this case, at least, that all these cohomologies are 0 whenever A is ample. So anytime you look at a divisor of the form canonical bundle plus an ample, then Kodaira vanishing tells you that its higher cohomologies are 0. And so because minus kx is ample, we can apply it here, and so we get that these are 0 by Kodaira vanishing. Okay. And now we can use these to compute the Picard group. So we have this exponential sequence. This is some sequence of now analytic sheaves. So we're using the analytic topology. This is the map x 2 pi I. And if you look at the long exact sequence associated to this, let's look at just the relevant pieces for the Picard group. So we know that H1 OX star, this is the Picard group, essentially by definition. From the long exact sequence over here, we have H1X OX, which we just showed is 0 in this case. And then over here, we have H2XZ, which is just singular cohomology. And then over here, we have H2XOX, which we also know is 0 from Kodaira vanishing. And so by the long exact sequence, this is actually an isomorphism. So kind of every line bundle is actually uniquely determined by its topological cohomology class. But then this tells us, like, we have a factorization like this, pick x to n1x tensor q, let's say rational or real, it doesn't matter so much. This maps to h2xq. And so what this tells us is this has to be an isomorphism, that basically numerical equivalence is the same as modding out by torsion in cohomology in this case. or maybe another way to say it is that if we just look at n1x with integer coefficients, this is pick x modulo torsion. And so in particular, because it's Picard rank 1, then this has to be z. And so our original pick x has to be z plus some torsion. And so we can just pick an actual line bundle that generates Picard. So we have a single line bundle, and because it's projective, we can pick an ample generator. Okay, and because this is an ample generator, and we know that minus kx is ample, then we know that minus kx has to be some multiple of this h. And of course, this all should make sense if you believe the theorem, because if you believe the theorem, then x is just P2, so Picard is just z generated by a hyperplane, and what's minus kx is going to be 3h. So that's essentially what we're going to try to do. We're going to try to show that this R is 3, and then use that to produce an isomorphism with P2. Great. And then here's a fact about Poincare duality. So again, here I'm secretly using that the intersection product under this map to cohomology is the same as like the pairing in Poincare duality. And so it's just a fact that if we take this this H, it's a generator for the free part of H2 of the singular cohomology. Then this implies that H squared is actually 1. You know it has to be some positive integer, and because it's really like the generator in H2, then properties of Poincare duality tell you this is actually 1. So we'll use that to actually compute. Okay. So let's do some computations. So if we look at H0 of this line bundle, OX of H, what did I want to say here? Right. Okay, so maybe I should have said first, let's compute H1 and H2. Okay, so this H2 by Serre duality is like H0 OX K minus H, but H is like 1 over R minus K. So when we subtract here, when we subtract H, it's like we're adding K. So this is H0 of some number D times K. But this is 0 because minus K is ample. Okay, so let's do the R strictly bigger than 1 case first, and then and then we'll go back to r equals 1. Okay, so in this case, this is 0. I guess h1 actually doesn't matter for what I wanted to say, because once we know h2 is 0, then we know that h0 is greater than or equal to the Riemann-Roch number, which if you compute it out is 1 plus r over 2 plus 1, using that h squared is 1, and using that k is minus rh, and this has to be greater than or equal to 2. So this tells us, in this case where r is strictly bigger than 1, then O of h has at least 2 sections. Okay, and then let's say D is one of those sections. Then we'll just compute, you can compute the genus of D with a junction. And if you work that out, you'll get 1/2 1 minus r plus 1. And what do we know about this? Since r is bigger than 1, then we know that this is strictly less than 1. So it has to be 0. So the sections of this h have to be rational curves. But in that case, if D is isomorphic to P1, then we actually know what R is, because the only R that makes this 0 is R equals 3. Okay, so let's recap the logic. If you assume that R is greater than 1, then you can deduce that R is actually 3, and that these divisors in the linear series of H are actually P1s. And now we'll just use that to produce an isomorphism to P1, to P2, sorry. So if we look at H0 OX of D mapping to H0 its restriction to D. Again, so here we have that H squared is 1, so this is OP1 of 1. So some similar idea to the previous one, where we'll produce a linear series by actually finding the P1 and checking that it restricts to O of 1. And then what's the next term here? Well, the next term is H1 of O, because this is the long exact sequence corresponding to OX goes to OX of D goes to OX of D restricted to D. But we showed earlier that that's 0. So that tells us this map is surjective. And now again, we use this to argue that it's base point free, because whatever base points exist for this linear series, they have to be on our curve, because they're the intersection of all the divisors in the linear series. But we surject onto H0 of O of 1, and O of 1 is base point free. So take any section on O of 1 that doesn't vanish somewhere, then we can lift it to a section of O of D that doesn't vanish at that point. So that tells us this linear series is base point free. So we have a map like that. And now we want to argue that this is actually P2. So basically, we need to know that H0 is actually equal to 3 rather than just greater than or equal to 3. So we know from this first line here that now that we know that R is 3, we know that this is actually equal to 3. So the question is, why does this h1 O of h vanish? Oh, and the reason, okay, yeah, the reason this h1 O of h vanishes now that we've computed a little more is by continuing this long exact sequence here. So Ox of D is a member of H, so this is the same as Ox of H. And if we continue the exact sequence, we have H1 X Ox maps to H1 X Ox of D, or Ox of H. This thing we want to show is 0. And then the next term is H1 of P1 O of 1. So this term is 0, and this term is also 0, so the middle term is 0. So kind of after the fact, this implies that this H1 is also 0, which means that this is an equality in Riemann-Roch, which means that H0 is 3, so this really is a map to P2. And now we have this map to P2. We know that phi upper star of O P2 of 1 is H. So phi upper star O P2 of 1 squared is H squared is 1. So phi is degree 1. So again, we have a degree 1 map that's birational. So it's bijective, and it's an isomorphism by Zariski's main theorem. Phi is degree 1. Okay, so that shows us that if the R in this computation of minus kx is greater than 1, then we really have P2. Okay, questions? So now we want to argue why it actually has to be greater than 1. All right, and this part is, I'll be even sketchier. This, we need to use some more Hodge theory. So if R equals 1, then we know that minus kx is equal to h. And then but we still know that h squared is 1. That was a general fact. So use what's called Noether's formula, which is just a restatement, or maybe I'll say a computation of Riemann-Roch using topological invariance. So if you plug into this version of Riemann-Roch, then you can compute that the Euler characteristic, topological Euler characteristic of X is actually 3. And then basically you derive a contradiction when you plug into Noether's formula, because you'll get that the Euler characteristic of OX is on the one hand 1 over 12 times minus kx squared plus e of x from this Noether's formula. But on the other hand, this is 1 and this is 3, and so this becomes 1/3, which is nonsense because it has to be an integer. Okay, so that was super sketchy, but if you write down these kind of topological formulas, you'll get this contradiction. So R had to be greater than 1, so we have to be in this P2 case. So then finally, use that, well, Kodaira dimension of P2 is minus infinity. And that Kodaira dimension of a curve times P1 is also minus infinity. So this you can check for yourself to see that in this case we had to be in the Kodaira dimension minus infinity case. Okay, so now I want to give a nice corollary of this. This is Castelnuovo's rationality theorem. Which says that a surface X is rational, i.e. birational to P2, if and only if the following two numbers are 0, h1 x comma ox, and h0 x ox twisted by 2kx. That's not so easy to read. Let me put it on the next line. So the criterion is that x is rational if and only if these two numbers are 0. And both of these have special names. So this is the Hodge number H01, and this is the second plurigenus. In general, these plurigenera are the global sections. Sorry, that was supposed to be a 0 here. These plurigenera are the global sections of powers of the canonical. Generalizing how for a curve, H0 of O of the canonical is the geometric genus. Okay, so that's the rationality criterion, and once you know MMP for surfaces, it's actually not so difficult. So I'll sketch it. So the first part, which again I'll relegate to an exercise, is that these numbers are birational invariants. Meaning that if I have two smooth projective surfaces that are birational, then they have the same H01 and the same second plurigenus. Okay. So let's take that as a given. That's somehow the easier direction, and that's one that doesn't really use the MMP. So then the harder direction is to show that, oh, I guess I should say, so once you know this, then if x is rational, it's birational to P2, and then you just compute that for y equals P2, the numbers are 0. So if you're birational to P2, then by this birational invariance, then the numbers are still 0. Okay, so the other direction is the more interesting one. So step one, we want to use this to show that Kx is not an F, because we want to use our understanding of these extremal contractions in the MMP, and that they always produce ruled surfaces or P2 to prove this. So our first step is to show that we can find such an extremal contraction. So to do this, let's write down some computations. So if we look at the Euler characteristic of OX, So this is always 1. H1 of OX was our assumption. This is 0. And then H2 of OX is the same as H0 of OX twisted by the canonical. But we're assuming that 2 times the canonical doesn't have sections. So the canonical can also not have sections, because if K has sections, then by just squaring them, you get sections of 2K. So this is also 0. And so the other characteristic is 1. Okay. And then if we look at the anti-canonical, then using stare duality, this H2 is the same as OX of 2KX, which again, by our assumptions, is 0. So if we look at the Euler characteristic of minus KX, it has vanishing H2, so Riemann-Roch gives us an inequality. And then the Riemann-Roch number is 1/2 minus KX times minus KX minus KX. So it's supposed to be D and D minus K. So it appears in Riemann-Roch, and here D is minus K, plus the Euler characteristic of O, which we just checked is 1. So now we compute this, and we get that this is greater than or equal to, or well, this is equal to, so the whole thing is greater than or equal to kx squared plus 1. Because here we have 2, we have minus kx, so we get a 2, and we get kx squared plus 1. Okay, so here's a lemma. If d is nef, then d squared is actually greater than or equal to 0. And d dot a is greater than or equal to 0 for a and ample. Okay, so proof, this is essentially by Kleiman's criterion. So the first one, well, if A is ample, then A is effective because some large enough multiple has sections. So D dot A is greater than 0 just by definition. And then the second one, by Kleiman's criterion, we know that if we take any ample, like this A, and we add any multiple of it, then we'll actually get something ample. So let me just add epsilon A, where epsilon is some small rational number. Then we know that D plus epsilon A, actually epsilon could just be some real number, because Kleiman's criterion is really a statement about the real cone. So we know that this is ample. So D plus epsilon A squared is strictly greater than 0. So then D squared, because this intersection product is a continuous function on the space of real numerical equivalence classes, then D squared is the limit as epsilon goes to 0 of this D plus epsilon A squared has to be greater than or equal to 0. Because this nef is in the boundary of ample. Nef is the closure of ample, basically. Okay, so that gives us that D squared is greater than or equal to 0. So our strategy is just to use this to check that K squared has to be less than 0, and therefore K can't be nef. So suppose the K is nef. So that this is greater than or equal to 0, then this has to be greater than or equal to 1, because here we had k squared plus 1. So this minus kx is effective. We can find some actual d. But then a times minus kx, where a is some ample, is strictly bigger than 0 because minus kx is effective. But on the other hand, it's equal to minus a times kx, which is less than or equal to 0 because kx is nef, so a times kx itself is greater than or equal to 0 by our lemma. Okay, so that's a contradiction. So kx can't be nef under these numerical conditions. I think I should just barely be able to finish. So now that we know kx isn't nef, now we run MMP, i.e. we produce these birational contractions. So we start off with x. We know we can find some contraction or some -1 curve. If we contract it, we know that we still get a smooth surface. So by birational invariance, these numbers are still the same. So kx is still not nef. So this tells us that we can keep contracting -1 curves until we get a minimal surface. Maybe x is already minimal, maybe x0 is xm, but either way we can contract -1 curves. And so xm still satisfies the same numerical conditions. Because these are smooth and birational. And so in the end, kxm is not nef. So then we know that there exists another extremal contraction here that's either a ruled surface or xm is P2, which implies, okay, so if xm is P2, we're done. Then we're rational, or phi is a ruled surface. But that tells us that xm is birational to z cross P1. And now again, we compute H1 x OX is the same as H1 z cross P1 O z cross P1, which is H1 of z. So z has to be genus 0. So xm is actually birational to P1 cross P1, which is also rational. So in either case, we end up with a surface that's rational.